Good morning, everyone. You are all very welcome. Let's watch the presentation of Khadija, and at the end, we will pass to the questions.
Good morning, everybody, and welcome to my presentation. My name is Khadija Al-Hassani. I am a PhD student working under the supervision of Dr. Mohammed Nasser Hanifa. My presentation titles as the new fractional linear multi-step method of order 4 with improved stability. Here, the brief outline of my presentation. I will start with the fractional initial value problem, and I will define the numerical approximation of the fractional derivatives and the superconvergence. I will give the main result of constructing two new types of fractional linear multi-step methods, and I will show some numerical test, and stability region and comparison will be given, and finally the conclusion. We consider the fractional initial value problem in this form, where beta is between 0 and 1, which is the real order. And this operator, the fractional operator, is the left capote fractional operator, which is defined here. In the numerical approximation of the fractional derivative, we define the shifted Grunwald approximation with the shift R. And it is known that this approximation is of the first order for any integer shift R, where this operator is the Riemann-Ribelli form. However, at a non-integer shift, when R equal to beta over 2, we have the super convergence of the second order, as it is given in this by this reference. So the shifted Grunwald approximation will be of order 2 for this kind of shift. So in our work, we apply the super convergence property to the fractional initial value problem. The solution of the fractional initial value problem N1 can be expressed by the Volterra integral equation of the second kind here. And one way to obtain the solution to the fractional initial value problem N1 is to approximate this equation by the convolution quadrature rule. This rule will obtain by Lubitsch, which obtained from the linear multi-step method for the ODEs, where this coefficient is the generating function, and this coefficient is the starting weights to compensate the reduction of order. Another way to approximate the fractional initial value problem is to replace the fractional derivative by in the fractional initial value problem by the Grunwald approximation, as it is given here, where this coefficient is an appropriate generating function. Like in the fractional linear multi-step method for the VIE, it's observed that the fractional linear multi-step method for the fractional initial value problem also fails to give the intended order for certain class of function. A remedy is to include the starting sum as it is given here. But the evaluation of this starting sum is very expensive task and causes difficulties in computation, as it doesn't affect the stability and convergence. So our analysis will be without the starting sum. Garab and Gallion and Garab established the equivalence of two types of fractional linear multi-step methods. We generalize their result in terms of the generating function. So by this theorem, which says that if the coefficient of the Volterra integral approximation are generated by this formula, then the coefficient for the method in 8 for the fractional initial value problem N1 will be given by this formula, which is the inverse of this. So the generating function for the fractional linear multi-step method for the fractional initial value problem N1 is therefore given by this formula, where rho and sigma here is the characteristic polynomial of the linear multi-step method for the classical initial value problem. Here we list some subclasses of the fractional linear multi-step method appeared in literature, and which is and this subclasses according to their generating function. The first one is the fractional PDF, which have this form of generating function. Another generating function of this form, which is obtained by Adams, which is the Adams subclasses obtained in this reference. The trapezoidal subclasses in this reference have this form of generating function, and the rational subclasses in this reference with this generating function. And Nasser and Khadija in the last presentation proposed a new subclasses of fractional linear multi-step methods which have this form of generating function. So the main work or the main result of our work is to construct a new type of fractional linear multi-step method of order 4 belonging to a new subclasses for the fractional linear multi-step method, which is not mentioned above. So to do this, we have this lemma. We will use this lemma. This lemma says that this form of function can be approximated with order 4 by this formula. Another lemma which is used in this work is this lemma, which says that the second derivative of a function can be approximated by the backward difference formula of order 2. We have the first part of approximation, and this is the second. This is the first kind, and this is the second one. And this can be proved by the Taylor series expansion. So we present the main result of constructing two new fractional linear multi-step method of order 4. The fractional derivative in 1 is replaced by the super convergence in 5 of order 2. And this gives a t equal to tn with the error coefficient of order 2 terms, as we can see here in this formula. The term t and t cube vanish with this choice, and the next error term will be of order 4. So we replace the fractional derivative in 13 by the fractional initial value problem n1, and we got this equation. As we can see, this term, which is beta over 2, since it is not an integer, so this term will be not aligned in the discrete point of the complex of the computational domain. So we'll approximate this part by using lemma 1. And here we have the second derivative, and we can use the first part of lemma 2 to approximate this part. So we'll get by this using this notation, we'll get this kind of schema. And again, by dropping the error term with this notation, we'll give the new implicit fractional linear multi-step method. This is the first one. Again, if we approximate the second derivative in 14 by using the second part of lemma 2, with the same operation and notation, we'll get another new implicit fractional linear multi-step method. And for the simplicity, we'll call the first one FLMM4, the first one, and this is the second one. So the generating function of our proposed method will be given by this formula, and we can say this formula of the generating function has not appeared in the previously known subclasses of the fractional linear multi-step method in literature. We apply our method to solve or to compute the approximate solution of the non-linear fractional initial value problem, where the source function is given here, and this is the exact solution. And the problem was solved for different values of order beta. Here, the computational order for the new fractional linear multi-step method, the first one, and we can see we got the order for each beta value. And here the another computational order for the second new fractional linear multi-step method, and we can see also for different value of beta we get the order 4. The stability analysis, for the stability analysis, we study the following linear test problem with the analytical solution given here. So the analytical stability, for the analytical stability, the solution y of t of the test problem is stable in the sense that it vanished in the beta pi angle region. So this is the region, the analytical stability region. But for the numerical stability, we have this criteria, definition. If we let S to be the numerical stability region of the fractional linear multi-step method for an angle alpha, which defined by this region. So the fractional linear multi-step method is said to be A alpha stable if this region belongs to the numerical stability region, and it is A stable if the analytical stability region belongs to the numerical stability region, and it is unconditionally stable if the real line belongs to the stability region. So the stability region of the fractional linear multi-step method of the forms in 16 will be given by this region, where S of C is the unstable region, and this delta of psi will be the generating function of the proposed method. And here the generating function of the first new proposed method, and this is for the second new fractional linear multi-step method. So to show the stability region, we draw the stability region of our proposed method. This is for the first method, and this is for the second method. This figure shows the unstable region for both of the method, and we can see from this figures that the unstable region suppresses the astable boundaries. This is the astable boundaries, and for all values of beta, which confirm that the method are not stable. Therefore, A by 2 stability and unconditionally stability could be the some measuring tools for the comparing the fractional linear multi-step method of order higher than 2. And we can see also that the unstable region are on the right side of the complex plane for many values of beta for both of the method, while it is peaks to the left side of the complex plane for some value of beta. So for comparison, we compare our proposed method with we consider the Lubitsch fractional PDF of order 4 and the fractional Adams-Moulton method of order 4, which their generating function given by this formula. For the A by 2 stability, we give this theorem, which says that for each fractional linear multi-step method, there is a threshold value beta star, which between 0 and 1, such that the method is A by 2 stable for this interval. So we compute the beta, this threshold value of beta star for each fractional linear multi-step method, and we can see that our method has the highest interval of beta, followed by the fractional PDF and the other the other method of new fractional linear multi-step method. And we can see also that fractional Adams-Moulton method has lower interval size in this sense. And this graph shows that the unstable region for the 4 methods for different values of beta. For this value of beta, all the 4 methods are the unstable region are on the right side of the complex plane. And as beta increase, still the 3 methods in the right side of the complex plane, while fractional Adams-Moulton method becomes bounded and falls in the left side of the complex plane and displaying only conditional stability. As the beta increase, the stable region, the stability region of the fractional Adams-Moulton method becomes smaller, as we can see, but while our method and fractional PDF stays in the right side of the complex plane and shows the unconditionally stable for many values of beta. For the computational efficiency, the weight of the fractional linear multi-step method have the simplest computational cost since they need only linear computations of the Grunwald coefficients, while for fractional BDF required computations by Miller formula with 4 previous weights. So in conclusion, we can say that we proposed 2 new type of fractional linear multi-step methods of order 4 for fractional initial value problem. The new fractional linear multi-step method are A by 2 stable for large interval of fractional order compared with the non-order 4 of fractional Adams multi-method. The proposed method also, weight outweighs the other method in terms of computational cost as well. And this is the reference that is used in this work. And thank you for listening. And this is the end of my presentation. And thank you.
Hi, Khadija. Our microphone were closed.
Yes, I open it now. Sorry about
Nice. Khadija, we had a lot of comments congratulating you for your presentation. And now we are going to start with the questions. The first one is made by Professor Edmund Capellas. Why not use Grunwald-Letnikov derivative instead of Caputo?
Yes, we are using the Grunwald-Lenktov approximation, especially the shifted one of the Grunwald approximation. The Caputo approximation is the Caputo derivative is on the initial value problem only. But to approximate, we use the approximation, which is the sorry for the yes, we use that approximation for this.
Okay. And now we have another question from Professor Felix Silva. Good morning. I have a question. Are there articles comparing these numerical methods with analytical methods?
Actually, we are using the approximation method for using this. We didn't go through the analytical method until now. So maybe in the next session.
Well, maybe because for non-linear problems, it's going to be hard to have the analytical. I guess so.
Yes, we are going to the approximation method, and we use the order for approximation method, and we get the very good result for this.
Very nice. Another one from Professor José Vantelé. Is there a better approximation for the fractional derivative and thus get more refined results?
Did they mean for the approximation that we used in this article?
Yes, I guess he's asking about other ways to approximate the derivative. Is this one very
difficult accurate? Or maybe no? Until now, we go for this. We didn't find another thing which is better than this, but maybe in the next study, because I'm still studying these articles, and I hope to get a better one. So.
Nice. Some comments here, Professor Edmundo. Me.
Thank you very much.
And another question. Let me see. Another one from José Vantelé. There are well, he did. There are several approximations for fractional derivatives. What are the reasons for the particular choice?
Yes, to get the order for approximation, which as the approximation have a higher order, the solution will get more accurate, and the convergence also be better than the previous. So we are concerning the order for approximation, and my scheme has a lot of approximation. That way to simplicity this approximation or these schemes.
Very nice. And another comment here. Interesting work. Very nice presentation. Let me see if we have another question. Yes, another one from Professor Adrian. How do you measure the error of the approximations?
Yes, we use a formula which which I cannot show it because of the time of the presentation. We measure the maximum error, and we use this formula to get the order of this. So I can show it later on, or I can give this error. I don't know how can I show it for you, but we use this formula to get the error of, or the order of the approximation. We measure the maximum error actually.
Okay, thank you. Well, we are running out of time, but we still have time for one last question. And I'm going to apologize with the other ones because we are running out of time. So the last one from Professor Paulo. How the value of beta interferes in the result? Is there any way of predicting this interference?
We choose this beta value. We make our computation with different value of beta. So as the beta is differentiate, the unstable region also get different and different for each scheme that we have used. But it is not interferes because we choose this beta.
Okay. So nice. Khadija, once and again, thank you for your presentation.
Thank you.
I invite you to answer the questions. The video of your presentation is going to be available here at SB Max page. And
Yes.
I invite you to answer the questions in the chat. Thank you again.
Okay,
I'm
thank
going
you.
to
I
stop the
want
presentation.
to say something last.
Ah,
I want to, I
feel
want to
free.
say a great thanks for you to give me this opportunity to present my presentation, and a great thanks for my professor, Dr. Hanifa, for his support. For his support, he support me a lot for this presentation actually. So I want to thank him, and thank you.
You are welcome. And Professor did a great presentation yesterday.
Yes,
So,
yes.
and I would like to ask to invite everyone for our last presentation, for our next presentation, which will start in 10 minutes. So it's enough time for us to have a small coffee
Yeah.
and a little break. See you soon. Thank you again, Khadija.
Thank you.
Pessoal,
Thank you.
até a próxima apresentação, que começa daqui a 10 minutos.